Hi there and welcome to PhD at Living. Today's a special bonus episode in our series about vision. Previously we've been talking about how the eye sees color, but today we're going to talk about how the eye is colored, and specifically with the iris. And no, not the iris that was apparently my favorite song ever according to my sophomore high school volleyball yearbook. The iris, which controls how much light gets to the retina in the eye, is composed of two pieces: the stroma at the front of the iris and pigmented epithelial cells at the back. And that brings us to melanin. The primary pigment in the eye is this chemical here, melanin. It's kind of a behemoth with this 5-ring structure, the heterocycles, the carbonyls everywhere, but the important part is the conjugated double bond system. What I mean by a conjugated double bond are two double bonds separated by a single bond. So for instance, double bond, single bond, double bond. The important part about melanin is there's a conjugated system, so I can propagate that conjugation all over the place. Double bond, single bond, double bond, single bond, double bond, single bond, double bond, single bond, double bond, etc., etc. What this does is allow energy and electrons to move very freely around the molecule. As far as I can tell, the back of the iris always has at least some melanin in it. The front of the iris, the stroma, however, can but doesn't necessarily have to have any melanin. It can also have some secondary yellow pigment called lipochrome. I couldn't really find the structure online and I don't want to give you a bad one, so you'll just have to forgive me. It's this combination of factors, how much melanin is in the back of the iris, in the front of the iris in the stroma, and whether or not lipochrome is present, that gives us all possible eye colors. Let's start with the really easy one first: brown. Lots of melanin in the back of the iris, lots of melanin in the front of the iris, and no lipochrome. That's pretty much it. Now let's go to the other end of the spectrum and albinism. Without any melanin or lipochrome in any part of the eye, you essentially have no color. However, most folks would say people with albinism have red-colored eyes. In the absence of any other color, what you're seeing are the highly concentrated blood vessels in the eye, and that's what gives the red tint. Now things get a little tricky. With blue, gray, and green eyes, we get the absence of a pigment that creates the color. Sounds kind of funky, no? The principles here are called Tyndall and Rayleigh scattering, and I've drawn a very, very crude example of the iris to try to show you how it works. When a beam of incident light comes into the eye, it can be either absorbed or scattered. With a blue-colored eye, there's a relatively normal amount of melanin at the back of the iris, but very little to no melanin at the front of the iris in the stroma. What this means is that the longer wavelengths of light, the reds and the oranges, go to the back of the iris and are absorbed by the melanin. The shorter, bluer wavelengths, however, hit the stroma and are reflected back out. These reflected, scattered blue wavelengths of light are what you see when you look at a person's eye that looks blue to you. Tyndall scattering happens when the size of the particles is pretty close to the incident wavelength of light. This means we're talking tens to hundreds of nanometers. Rayleigh scattering, on the other hand, happens when the size of the particles is significantly smaller than that of the wavelength of light, so tens to single nanometer size. There are many different biological compounds that live in the stroma, collagen, hemoglobin, etc., so there's probably a combination of Tyndall and Rayleigh scattering that gives you the overall color effect. Not to get into the weeds, but this Rayleigh scattering is literally why the sky is blue. We'll get there sometime, but not now. Let's talk blue eyes. With very little to no melanin in the stroma, the longer wavelengths are absorbed at the back of the iris, and the shorter, bluer wavelengths are spat back out. That's why someone looks like they have blue-colored eyes with no blue pigment. Gray-colored eyes are very similar to blue-colored eyes, except for having maybe a little more stuff going on in the stroma. This causes different Tyndall and Rayleigh scattering, which causes different colors. Other than that, gray-colored eyes and blue-colored eyes are pretty much the same. Green-colored eyes can be considered blue-colored eyes plus, the plus being lipochrome. When the blue scattered rays from the stroma combine with the yellow lipochrome rays, thinking back to kindergarten, yellow plus blue equals green. Hazel and amber-colored eyes are kind of all over the place. The amber color, which is relatively rare in humans, probably has as much if not more lipochrome in the back of the iris as it does melanin. That's what gives the amber-colored eye its brownish, yellowish, orangish amber color. Hazel, on the other hand, definitely has lots of melanin in the iris at the back and in the stroma at the front, and probably has little splotches of lipochrome in there too, which gives the hazel this kind of hard to define color. As a special extra bonus, do you know what causes that red eye effect in pictures? It's a combination of your pupil being too open and the flash on the camera being too close to the lens. Essentially, your pupil doesn't have enough time to close, so you see the blood vessels in the back of the eye. As we know with the albinism discussion, blood vessels look red, and that's really all that causes the effect. And that, my friends, brings our fun-filled discussion about vision to a close. See you next time! You know the thing about a shark? He's got lifeless eyes. Black eyes, like a doll's eye.